Welcome to this module of the ZK Whiteboard sessions. I'm Nico, I'll be today's host, and our guest today is Vadim Lyubashevsky from IBM. Hello, Vadim.
Oh, hi, Nico. It's a pleasure to be here.
Yeah, it's a huge honor to have you here, especially to talk about today's topic, which you're a leading expert of, which is?
Lattice cryptography, and in particular, lattice proofs, where we try to actually do proofs compactly and with efficient verification. So in this session, we'll try to cover, as much as we can about, first we'll introduce lattice problems, so the hard problems that we think, are computationally hard even for quantum computers, because that's kind of the main draw of lattices. One of the main draws is that they're computationally hard for quantum. Then we'll talk about how to get commitments from these problems. Going to be pretty straightforward, but it's its own thing. And then compact commitments, how to commit to a long string sort of compactly. And also, very importantly, to prove knowledge that you know this long string. That you know that it's long, that it's the string, and that its norm is short, which is pretty important for lattices. Then once we do that, then we're going to actually try to prove more exact norms of this. So as we'll see with lattices, it's a two-step process. First, you prove that something is kind of small, so you know it's a commitment, and then you kind of get into it and say, actually, the norm, use some more techniques to prove that the norm actually is as small as you kind of desire, as long as you had it originally, right? There's no relaxation in what you prove. So we'll do that, and we'll actually prove that'll be almost, the complete high-level introduction to how one would do these proofs in practice, these lattice-based proofs in practice. And then we'll switch over to maybe an even more high-level overview of how you would do this even more efficiently, instead of over integers, over polynomial rings, which is what it's done in practice for all other lattice-based schemes. And this is very compatible with the proof systems, which are not going to be zero knowledge at this point, but they can be made zero knowledge using some other fairly standard by now techniques.
Sounds good.
Okay, so I guess the very first thing we should know is what is a hard lattice problem, because we will need something like commitments for proof systems. So we will need a hard problem for that. So let's first kind of describe what a hard lattice problem is. So in general, we work. It's a linear algebra thing. So we work with matrices A, and they're usually in some. Let's work over integers for now, but in practice, we really work over polynomial rings for efficiency.
Okay.
But we will maybe if we have time, we'll talk about that later. But hopefully, a lot of the techniques carry over. Okay, so we have some ZQ, and Q is usually a prime. Let's say of 2 to the in these schemes, it'll be about 32 bits, 48 bits. In encryption schemes, it's smaller, but let's just Q is something like that in ZQ, and it's like n times n. So n is usually tied to the security parameter. So and in practice, it's about 512, 1024, something like this. M can be whatever you want. Okay. And then there's the secret S, and it's a vector in z to the m with small coefficients.
Okay.
So the norm of S is small with respect to Q.
Okay.
So you could think of S as being binary, maybe, but it could be bigger than that. Just this has to be small with respect to Q.
Is S a vector in ZQ or just Z? Doesn't matter.
Doesn't really matter, right?
Okay.
Because you think of it however you want. We'll do operations mod Q. You can think, because we're assigning some norm to S, we can think of it as integers. But if you want to think of it in ZQ, that's fine as well. Whatever's easier. Okay, and the one-way function is so FA of S equals AS mod Q. Okay, so that's it. I basically take S and I multiply it by A, and that's my one-way function. So it's hard to find S given FA of S, given this T.
Okay, FA and A, and it's hard to go back to S, right?
Exactly. You're given FA of S and A, and it's hard to get S. Exactly. So this is called the SIS problem, the small
SAS.
SAS. Basically this. So this is the inhomogeneous version, meaning that this part is not zero.
Okay.
You can also have the homogeneous version, is when you're given an A.
Yeah.
Given A, a random A, find S such that AS equals 0. I'm going to stop saying mod q because everything's mod q.
And AS, this is the zero vector.
This is the zero
okay,
vector.
Cool.
Yeah. And I'll probably stop writing vector
Yes.
signs.
Sounds good.
Okay. Because I'll forget. Okay. Good. So this is the
hard problem.
The SAS problem. Right?
Okay.
Okay. And so one thing you may kind of see immediately is that this is already you can get a commitment scheme like this, and a compressing commitment scheme. So all you do is you multiply. You have your A.
Yeah.
You multiply A by S equals T, and you say T is a commitment of S. And the reason it's binding is because if you find another AS prime equals T, then this implies that A times S minus S prime equals 0. And the norm of this is basically twice as large as the norm of S, which is still small with respect to Q. We set our parameters, so this is still a hard problem.
Okay.
And this is now a solution to this. So basically somebody who can find a second preimage solves this.
Okay. So our commitment scheme is just multiply the vector we have by A,
and that we've committed to A. Yep. And notice that since I said before that M could be sort of arbitrary, almost arbitrarily large, this is a compressing commitment. So you could have a very long vector S, so basically of size, dimension M. Yeah. But at the end, you get a vector T that's of dimension N.
Okay.
Now, the coefficients of T are bigger because S had small coefficients, but this has coefficients all the way up to Q. But that's not a big deal, right? That's a log Q difference there. Yeah. But you do have a big compression from M to N.
So is this what we call the ITI commitment?
Yes, exactly. Okay. This is the ITI commitment. So from 1996, this is the original ITI paper where he said actually being able to solve SAS is as hard as solving some worst case lattice problems, and kind of that gave us the framework to build on, to care about this SAS problem specifically. And we said, okay, now let's actually analyze this SAS problem. Okay. But yes, exactly. Okay, so now that's kind of all the tools we need to start building our proof systems.
Nice and simple.
Yep, exactly. So yeah, there's actually a lot less math here than you need for other things, right? This is basically all you need to know. Okay, good. So now I guess we're not going to get into the most efficient schemes, but we'll try to just give an idea of how you can get a succinct proof system with an efficient verifier to prove something that's interesting. So the interesting thing will be, so suppose, and this is very basic, suppose we have some vector S. We want to commit to this vector S. It's a very long vector S. Yeah. And we want to prove that the norm of S is some bounded thing. Is some bound. So that's all we're going to prove. We can also, like for real systems, we can also add some linear equations into it. We can also prove that S satisfies blah, blah, blah. But that's not that's kind of let's say the easy part. Okay. Proving linear relations is pretty easy. Yeah. It's proving this norm of S that's always the tricky part.
And this
quadratic
is
relations
necessary because our problem is only hard when the norm of S is small, right?
Exactly. If the norm of S were large, then it's actually pretty easy because we have if you draw your A, we have your A times S equals T, right? Then if there's no size restriction on S, then you could just, pick a square part of A that's invertible, right? Set all of the rest to 0. Right. Right. And then, so you ignore this. I see. And then you just have A times something equals T, and using Gaussian elimination, you find this something, right? I see. So, yeah, so it is quite crucial that the norm of S is small. And that also, it's annoying, but I think that's also what makes this SAS problem plausibly quantum safe. So that there is this size restriction on S that seems to make it very different than discrete log and problems of that form. Okay, so we've described commitment schemes. So now let's actually commit to S and prove to a very long S and prove that we know it and that its norm is small. Sounds good. Okay. So we have this long vector S. Let's say it's size m squared. Okay. So little m squared. So what we're going to do is we have our matrix A, right? Which is, you remember, A is in m by n. And we're going to break up our S into m parts of m dimensions each. Okay. So now we have a matrix like AS1, S2, all the way up to SM. Right? These are vectors.
Yeah.
I've given up on the arrows.
Yeah, that's fine.
It's not going to happen. And this, exactly, each of dimension m.
Yeah.
And this is equal to like T1, T2, up to Tm. Right? And these are all vectors of, again, dimension m. Okay.
So can we understand this as doing A times S1 equals T1, A times S2 equals T2?
That's exactly what it is, right? And now observe that this commitment is now smaller, right? So before, if each S was m had dimension m, then this was m squared.
Yeah.
But now this is n by m, and n is the security parameter, right?
Yeah.
So it's kind of independent of m for the most part. Okay, so our commitment is now smaller. Okay. Good. So, and then, instead of writing this, I mean, you can think of it like this, but I'll write it as AS equals T.
Okay.
Okay. And it's all mod Q. Let's not forget this.
Yes.
Okay. Good. So now I want to prove to you that so I have this T. I want to prove to you that I know some S, so that S satisfies T. All right. So let's just do kind of a bit of a thought experiment that's almost a proof, but it's going to be a proof. All right. So now the verifier gets A and T.
Yep.
And what he does is he sends a vector C. So C is in a random vector in 0, 1 to the m.
Okay.
Okay? All right. And the prover responds with Z equals S times C. And he sends the C. Now, the verifier then checks that 1, norm of Z is small. So in this case, like what can we hope for small being, right? Notice that we have our S, which, let's say S is binary, whatever.
Okay.
Right? So if S is binary, then each coefficient of SC is at most M.
Yes, because at most we have all ones in our C and we're adding everything together.
Exactly. Okay. Exactly. So each coefficient is at most M. So that's something he could check. He could check the L2 norm is M times square root of M, right? Because we have M of these dimension, right? So small is just, I'm not going to write precisely what it is, but it's just small depending on what we're trying to prove about S.
Sounds good.
Okay. But again, small it has to be small enough with respect to Q so that the cis problem eventually is still hard. We'll get to this, how this relates to the cis problem.
Okay.
Later.
So we keep it vague for now and we'll come back to it later?
We'll make it less vague.
Okay. Sounds good.
It'll still be vague, but
not completely.
Maybe at least one can fill in the blanks.
Sounds good.
Okay, and 2, we check that A times Z equals TC. And notice that if T really is AS, then this should verify. Okay.
We have ASC on the right, and here Z is also SC, so ASC.
So ASC, ASC. Okay.
Sounds good.
Okay, good. So the protocol is at least complete, right?
Yes.
Okay. So now why can we hope that it's sound? All right. Now suppose that, so we have our Z that satisfies this, and now suppose that the prover can also answer this query for another C, for a C, let's say for a C prime, that's the same as the C here, except in the ith coefficient, it's flipped. Okay. So if the ith coefficient of C was 0, the C prime is 1, okay. and
Could we write maybe a very quick example of the two of them?
Sure. So if C is the vector, I don't know, 1, 0, 1, 1, and we want to flip this position, then this C prime would be 1, 0, 0, 1. Cool. Okay. So now you notice that C minus C prime is going to be 0 everywhere except plus or minus 1 in the position that's flipped. Yeah. All right. So if the prover, I mean, that's a big if. Yeah. If the prover can actually answer for this as well, then we'll get the file. We'll get so we'll have Z prime equals
SC prime.
SC prime.
Okay.
Well, no, we don't really know that the Z prime is SC prime. Z prime is something. And Z prime is small. And AZ prime equals TC prime. Right? So now we have AZ equals TC, AZ prime is TC prime. Subtracting, we get A times Z minus Z prime equals T times C minus C prime. Now, notice that C minus C prime is exactly, 0 everywhere except the ith position. So this is actually ti, right?
Or minus ti, I guess.
Yeah, exactly. Or minus ti, exactly.
Yeah. Cool.
Right. So then we have a times something that's small equals plus or minus ti.
Right.
So and that's actually, so we do know something. So now, of course, the size of z is bigger than the size of s. So what the prover knows something, but he can only prove that something's a bit bigger.
Yeah.
But for now, we don't really care about the size. We just care that it's committing. So it's like I'm small enough, right? We're gonna end up proving that something about the norm of s that's actually much smaller, right? But for now, we're just trying to say that he committed to something. There's only one thing he can open to.
Okay.
Okay.
So just in this case, this would be Si?
Well, it's the extracted. So let's call this like S bar sub I. That's not the Si. So he knows some Si, which is maybe binary, right? But now the Z's have coefficients size, as big as M, right? So now this A times Si equals Ti. This is not.
Okay, this might not be exactly Si.
He may not prove that he knows Si, but the important thing is he cannot open it any other way.
I see.
So there's only one thing. Maybe he knew something that was much bigger, right? And that's what he proved, right?
Yeah.
But whatever. So there's only one thing he could have opened to. We still don't know about we can't still ascertain that the size is as small as he claims, but we know that there is only one thing he could have opened to.
Okay.
Yeah. This is clear. Okay. So let's. So that's good. But now let's. So now we have like two things to discuss here. One is, well, this doesn't really. This isn't. We can't really expect the prover to do this, right? Yeah. Because let's say the prover, some adversarial, he only needs to succeed with probability less than a half. He can say, no, look, I will only answer this challenge if this is a 0, right? He'll just fail, actually because he cheated on the TI, right?
Yes.
Okay. So then the solution here is, well, here we sent a vector C, but what if we send a matrix C, right? So here what we did is we sent a vector C, right? That was 0, 1, right? And then the extraction, we fixed C everywhere except one position and flipped that.
Yes.
And that we said, well, the prover may not answer that. But what if we instead send a lot of challenges C, so like a matrix C, right?
Yeah.
And then Z was S times capital C, right? So basically sends a lot of these Z's, right? And now all we have to do is we fix everything in this matrix, except we make this last row completely random.
Random.
So we make it 0. So we don't necessarily flip it, but we say it's just random.
Okay.
Okay. So now now since there's, let's say, 128 of these, now he has to reply. He cannot just not succeed on all of them, right?
Right.
Okay.
Because if not, we do have a sound protocol.
Exactly.
Right.
Exactly. Okay. Because then he probably just is not going to succeed very often.
Yes.
Prover, right. And so now with high probability, one of these will be flipped, right? And for that one, we extract.
I see.
Our Z. Okay. Right. So now, of course, the downside is now this is much bigger, much bigger.
So just to resume this step, the problem we had here is if the prover notices that we have a flip, they might just abort.
Yeah.
And it's not a big deal to Soundness because they still have 1/2 chance to win.
Yeah.
And then here we force it to become much larger.
Yeah, exactly. Okay. So it's not even notices, right? It's like he says, look, I actually cheated on position 3.
Right.
Right? So like I will only reply when it's 0 because I have no idea what it actually is. I need my S to be multiplied by 0.
I see. Right? Okay.
Or it's like S is actually huge and I need it to be, or let's say, it's something.
Okay. So if our challenge is such that position where the prover cheated is 0, then prover is happy to go.
Yeah, exactly. Okay. Like, let's say the S in that position is actually huge, right? But he's like, oh, that's fine. That's great. Because as long as it's 0, it doesn't contribute. So he's like, that's all I'm going to answer.
Okay.
And good, he'll succeed with probability 1/2, right?
Yes.
So it's actually not just a proof, problem with the proof. It's actually insecure, right? But here, if he says the same thing, he's like, oh, I'm going to, S is large and there's not, you'll never catch. Well, that's not true. We will catch him, right? Because one of these will be 1, right? And he has to answer.
Gotcha.
If he's waiting for all of these to be 0,
never going to happen.
Never going to happen, right?
Okay.
So that's the intuition. I mean, yeah, this is the intuition if you really want to do this over the integers, right? But we never do things over the integers. But I think this idea of kind of fixing everything except one thing that has a large entropy and changing that actually is used in our techniques a lot, lattices a lot. Okay. So yeah, so now, okay, so good. So now we modify this protocol. So instead of this being a vector, now this becomes a matrix in M by, let's say, 128, whatever, doesn't matter, some security thing.
Yeah.
And this is Z equals S times C. This is now a vector, matrix. Sorry, now we can check that, whatever, norm of Z is small, let's say all the coefficients in the matrix are small, all the column, again, being as vague as before.
Sounds good.
Right? And then this is AZ equals TC.
Okay.
And then the proof actually goes and this time it actually goes through.
Okay.
Yeah, because now we do know that there is some C that is flipped in one of the, and that's exactly what this C is. Okay. Good. All right. So this
Does the intuition for the proof look the same?
It's exactly the same, right? Because what we're going to be saying is that there is some column where this bit really is flipped.
I see.
Right? So they actually, before we said if there was one, then we could extract, right?
Yeah.
But there didn't have to be. Now there must be one. Okay?
Yeah.
Good. All right. So now, we did this. And so now we know that there is some S. So what we did is we extracted some A times S bar, which equals to T. Because we do this extraction for every position.
Okay.
Right? And this S bar was the Z minus Z.
Yeah.
Z
so
right?
This thing of having two columns that are flipped, we apply that to every position.
Exactly.
And that's our S bar matrix.
And we extract, we apply to position 1 through M, and we actually extract our S bar matrix.
Okay.
Okay, so now we can extract AS bar equals T. Okay, and now we're going to claim, so this S bar is not the same as the S, but it's something. Okay, now we're going to claim that this Z, right, this Z must be S bar times C.
Okay.
Okay, so my claim is that Z, claim, Z equals S bar times C. Okay, and the reason for this is that we know that AZ equals TC, right? And we know that T equals AS, so we have AZ equals AS bar C, right? So we have A times Z minus S bar C equals 0.
So let's see. We
had AZ equals AS. So we know that T is A times some S bar, right?
Sorry. So we said T equals AS. Why do we have the bar here?
Because we extracted the S bar.
Yes. Okay. Sorry, I was looking up there.
That AS is something we claim we have, but all we can do is prove S bar.
Okay.
Okay.
So we substitute AS bar for T, and then
Yeah. So Z must be this S bar times C.
Yes. Otherwise, we have a problem with our binding.
Exactly. Otherwise, we have a solution to cis. Actually, we have many solutions to cis, right? Because this is now a matrix, and we have like 128 solutions to cis.
Yes.
Okay. So this is small, and so this is 0. Okay.
Sounds good.
Good. So let's just remember that Z is now S bar C. Okay. Good. One additional thing that we'll need is that something kind of obvious. Is that, let's say I committed to the S, and I also want to prove that this S satisfies some other linear relations, like some B times S equals Y.
Okay.
So let's say I want to also prove that BS equals Y. Well, this is pretty simple, right? All we have to do, the verifier just has to check that BZ equals YC, because look what we have. We have A S equals T, right? So this is what we have.
Claim.
And let's say I also want to prove that I want to kind of append this B underneath the matrix, right? Equals Y. Right? So then I do the exact same thing. I send the C, the Z. The fact that the S bar is kind of committed to, is this unique, and that Z must be equal to S bar C comes from cis, from this. And then this part is just you check that you just have to check that B times Z equals YC. Like if
Okay,
you
so
think of,
we are redoing this again, but for
Exactly.
b and y.
exactly, if you want, you can think of A and T as like being like this is now A and this is now T, right? And we've extracted
Yes.
the exact same thing. It's just the top part is needed. At some point we have to argue cis, right?
Yes.
So here we need this to be random. So we can argue that there really isn't a unique S bar. But this part can be whatever you want. It doesn't have to be random. Doesn't like once you've established that there's this S, the extraction, the fact that B times S bar satisfies Y is exactly the same extraction as here, right?
Nice.
So yeah. So now we can commit to so we've seen a commitment scheme, right? We can commit to something that's m squared size and kind of the commitment size is O of m.
Yeah.
And we can prove that we know some opening, right? It's quite large, but but we haven't really proved that the norm of S is something small, right? We do prove that the norm of S is not too large, right? It's like m, like each
small with respect to the cis problem.
Yeah, but it's not really as small as we claim. Let's say if I wanted to prove that the norm, this was binary, and I'll prove that the norm is really like, I guess m. If h coefficient is m, this doesn't do it because this proves that each coefficient is m, and this is not quite what we want. Okay, so now we're going to use this kind of to prove that like this tighter relation of the norm, and the way we do this is this idea. I mean, it's kind of we've been building up to it, and now we kind of just noticed that this is actually what we've been doing, and we're kind of calling it the left-right technique or left-right proof, and we'll kind of see why it makes sense. So this is the proof on the right side of S, right? Because we're multiplying on the right. And now we're going to try to do something from the left side. Now that we've established that Z is something, we're going to try to prove something about it from the left side. And you'll see why we can't just work with one side, and we have to have both.
Sounds good.
Okay, I think now we're actually ready to present the full protocol. All right, so let's leave, so let's just remember what we can do here.
Yeah.
Right, and I'll remind you when we get to that part. And okay, so just our statement is, right, that we have an S, we committed to S, that AS equals T. And also we want to prove that the norm of S, that's actually the norm of S squared, it's easier. Equals some beta.
So what do we mean when we say the norm?
Yeah.
Like what does
it
look like?
Right. So the norm of S, the norm of this matrix, it's not really the matrix norm because there's a notion of that. Here I just mean simply the norm of all the kind of the sum of all the norms of all the vectors. So for example, if the coefficients of this matrix are like I don't know, like A1, A2, A3, whatever, then it's just A1 squared plus A2 squared plus A3 squared, etc. So for example, if we treat, these are vectors, right? Then it's basically norm of S squared is the norm of S1 squared plus the norm of S2 squared.
And then the norm of a vector would be?
The norm of a vector, if the vector like S1 equals like A1, AM, right? It has M coefficients, then the norm of S1 equals A1 squared. Okay. So it's just the
sum of the squares.
The sum of the squares. And I guess importantly in the next step is that here these S's are columns, right? But next we're going to be we're looking at this vector matrix S. We're actually looking at the rows. But it's the same thing. The norm of S squared, since it's just the sum of the squares of each coefficient, it'll be the norm of the row squared, reverse row squared plus the norm of second row squared, etc. Yeah. It doesn't matter how we split. Right.
Sounds good.
Okay, so we'll be trying to prove that this equals beta. Okay, and
just a quick question: where do we have the norm squared?
Why do we have the norm squared? Oh, because the norm would be the square root of this, and we don't really want to take square roots.
Sounds good.
Right.
Yeah.
So yeah.
For convenience, I guess, or
because we actually don't, because what we actually know how to prove is the norm, right? So something also to notice, right, that the norm of like some S1 squared is, you can think of it as the inner product of S1 with itself, right? Which is just notation for, just if you take a vector and you do the inner product, you just multiply this element, right? So like you have S1 times S1 transpose, right?
Yeah.
Then it's just
Yeah. So we do the sum of the squares. Nice.
Exactly. All right. Good. All right. So I'm going to start the protocol from step 2 because step 1 kind of will be clear what.
When we get there later.
Yeah. When we get like, this is what's missing, and that's going to be step 1.
Okay.
All right. So
maybe we can write 1.
Yeah.
Leave it there.
1. Question 2 is the verifier. So I'll just write V. Sends a random sends lambda, random lambda in ZQ. So just an integer in ZQ.
Yeah.
Yeah, maybe even ZQ star, so 0 is not included. Doesn't matter.
Sure.
Okay.
Unlikely to happen that we get 0.
Well, Q is not that large, right? Q is like 2 to the 32, so maybe you should say Q star, but okay. And now the prover computes, so what I call U plus and U minus. Okay, so now U plus is, so let's write it here. U plus is the sum from I equals 1 to M of, okay, so now we need some notation for, like I said, the rows of S.
Yeah.
Right, so I don't know, we can call them like S squiggly.
Sure.
So S squiggly is the rows of S.
Okay.
S of I times lambda to the I. So lambda to the I times the row. So we basically sum up the row, weighted sum of rows. So the first row gets multiplied by lambda, second row lambda squared, etc.
Okay.
Now U minus is I equals 1 to M of lambda minus I, the SI.
Okay.
Squiggly. Okay.
Why are we doing this?
Because, so now notice that these are just vectors.
Yeah.
Right? So now we're going to take the inner product of these vectors. If you notice that U plus U minus, right, is, if we do the multiplication.
Yeah.
So now let's
okay, I guess we can write it out, right?
Well,
lambda I times lambda I minus I times S squiggly I.
Yeah, so
S
like,
squiggly,
yeah, it's a bit annoying to write out,
okay.
but we only care about like some important, here's the important thing we care about. That, so we do this product, right? So now for the I, for the same I's, the lambda, the powers of lambda to the I will cancel out, right?
Yes.
So we will have something like sum from I equals 1 to M of Si, right? We will have this.
Yeah.
So because the powers will cancel out.
When they're equal. Yeah.
Then, now what are all the possible powers of lambda? I mean, I guess they range from like M to minus M to M, right? Yeah. Plus sum from negative M less than or equal to I less than or equal to M, and then I is not 0 because the 0, I equals 0 is kind of, the power is covered here already.
Yeah.
Right?
Yeah.
We have, you said it was easy to work out. Go
No.
No idea, right? Yeah, exactly.
Sure. Okay.
It's something, right? It's like, maybe like S, the power of lambda to the 1, right? We'll have like S, I don't know, 2, and with S1, with S1, right? Yeah. And then also S3 with S2, right? So something, right? But it's basically something that we don't care about, right? So let's just call this this is some function of S1 through Sn.
Okay.
Right? Times lambda to the I.
Okay. And I guess GI it's going to be different ones every time.
Exactly. Thank you. All right.
Cool.
So we will have this. And now the important thing is notice what this is. This is exactly beta, right? Because we're taking the inner product of the first row plus the inner product of the second row plus the inner product of the third row.
And we said that the norm squared was the inner product of the row itself.
Exactly. The sum, right, exactly. So the sum of all the inner products, that's the norm of S.
Cool.
Okay, so that's beta. Yeah. And this is something we don't care about. But the important thing is the number of these terms that we don't care about is like 2m.
Okay.
Okay.
So it's not as big as our original matrix.
Exactly.
It's not m squared.
Exactly. So what we're going to do is we're going to send in the first step all the GI to the S1 Sn. Okay. So I guess maybe you see where we'll be going with this, right? At some point we'll prove that actually what we have is this, right? Which implies that this part that the inner product norm of size must be beta, because this basically Schwarzschild.
I was going to say, we see a polynomial here happening, and we see, I guess, two ways of computing it, right? With these guys or with the claim and the G's.
Yeah, exactly. So these guys, right? If we can prove that that these guys are somehow, actually the S's that are committed to here, right? Then we have proven that, and if we've proven that this is like beta plus lambda to the I, then we've proven that this part really must be beta.
Okay. Right? I guess I'd see how it unfolds.
We can get to that. Yeah, exactly. But that's the kind of I guess maybe you're seeing, right? Because the lambda to the I is the X, right? So we have some polynomial in X. Okay, good. Okay, but so the intuition is, right? If we know that this is already somehow related to S, right? These U plus and U minus.
Yes.
Then we can prove. But we don't know yet that this is related to S.
Absolutely.
But this is actually what we have done in the first step, right? So let me just notice something here. Notation. I'm going to write this. Notice that this is. I'm going to write the vector lambda, which is just lambda squared. Lambda to the m, and like lambda minus is just. So this is actually lambda times S, and this is lambda minus times S.
Okay.
Right?
Just notational.
Just notation. I did nothing, right?
Yeah.
I just sort of wrote this as a matrix vector. Maybe we don't even care. Okay. So now once we did this, now we have to somehow prove that, hey, actually what we were doing before was like this S somehow is connected
to the U plus and U minus?
To the U plus and U minus, exactly. So then what we do is that the prover, the verifier, and sends them.
Yes. I guess implicit to...
Yeah. I've been writing send here, but yeah, just to make sure. Okay, so the verifier sends... Now we're doing this thing that we saw before on the left, on the right side.
AS equals T, okay.
Exactly. Sends C from like this 0, 1 to the...
we said 128 or something.
M times 128, exactly, something like this. And the prover sends Z equals SC. Okay. So now the verifier has to perform a bunch of checks. Checks. Okay. A. So he has to check that AZ equals TC.
That's from our previous...
Yeah. So that... Okay, right. He checks that lambda times Z equals U prime, U plus times C. He checks that lambda minus 1 times Z equals U minus C. Okay. Let's see. Then he checks this thing, right? That
this here, right?
That U plus with U minus equals beta plus sum of lambda I gi to the S1 Sn. Okay?
Right.
So the first three things establish that Z really is that Z really is some S times C.
Some S bar, right?
Some S bar, yeah, exactly. Okay. Some S bar times C, right? And now, and this last part, and also that S bar satisfies lambda times S bar is
U plus.
U plus, lambda times S bar is U minus.
So is this sort of the linear constraint thing you were showing us earlier as well? Okay,
exactly.
So we have A, and this would be our B.
Exactly,
and our Y.
exactly.
Okay.
That's why I mentioned that you can actually just for free prove a any linear relation you want. So we set up the linear relation we care about here.
Yeah.
Right? We prove that this S satisfies it. So now we know that that lambda times whatever S we extracted from here is really U plus. We know that lambda times this S bar equals U minus. And so now we do this inner product, right? So whatever we committed to, now its inner product is beta plus whatever, right? So now is it kind of, now do we see why this implies that the norm must be beta, right? Because, so if you think of this is some polynomial in X. So if you write like f of X, like what the prover does in the beginning is he defines this polynomial by sending, by sending these terms and the beta, right? So you wrote equals like beta, that's the constant coefficient, plus sum of whatever, negative m less than I less than mi not equal to 0 of x to the I, gi of all these some coefficients.
Yeah, exactly. This is a coefficient.
Yeah. Okay.
The only question I have is this still a polynomial when we have negative powers?
Yeah, because you could, I mean, it's still, because I guess you could always multiply by x to the m.
I see.
And as long as x is,
everything.
Exactly. As long as x is not 0, if the one is satisfied, the other one is 2, right?
Sounds good.
Yeah, you just multiply. Okay.
Yeah.
So all we care about is the number of solutions to this. I hope that's right. Right. So we have this whatever f of x, polynomial. I don't know. So we have this f of x is this, and now what we've implicitly done here is we've evaluated this polynomial at some lambda, right? And we said f of this lambda is this.
Yes.
So then we're saying it must have been that polynomial, right? But like, maybe not, right?
Yes.
Maybe there was another polynomial. Maybe the correct polynomial is something else, right? Maybe
just so happens
equals something that's not this.
Anything else.
Like not equal to f of x, right?
That's how we write it. Yes.
It's not equal to f of x, right? And maybe it happened to be that f of lambda equals f prime of lambda.
Yeah.
But of course, then this implies that f minus f prime of lambda equals 0, right? So if we subtract them off, it's another polynomial. F prime. So now we have this polynomial f minus f prime of lambda equals 0. But this cannot happen too often, right? Because the degree of this f, once we kind of shift it, right, is 2m.
Yeah.
And the same thing for f prime. And so the
probability of this thing being the 0 polynomial is very, the probability that this is non-zero and that at lambda it was 0 is very low.
Exactly.
So this is our third zipple.
Exactly. It has at most m roots.
Yeah.
Right?
Yeah.
2m roots, right? So the probability that this is one of these roots is 2m over q.
Yeah.
Okay. So if q is not so big, you will have to repeat it a bunch of times, but this is, I don't want to talk about that too much because this is the integer, this is over the ZQ, and we don't really do that for efficient things. Okay, so now that's it. That's the protocol.
That's it.
Are we done? Did we prove what we wanted?
Actually, before we get there, I had one more question, which is, when we did the version with just AS equals C, the verifier in the check needed to check that the norm of Z was small.
Yeah.
Do we still need to do this here?
Did I forget this? Yes, I did.
Okay.
Thank you. Checks that norm of Z is small.
Okay.
Sorry. Thank you.
Then all good. And then to your question, does this solve our problem? I guess if you're asking, it means no.
Right.
Yeah.
So almost, right? But actually, like, there is this one part that seems like, well, it's obvious, but it's actually a little bit tricky, right? So because maybe because of all the because I dropped the notation. So I dropped writing mod q everywhere.
Yes.
Right. So notice everything is mod q here. So what I've proved is that basically the sum of SI, these inner products, the sum of them is beta mod q, which is not the same as beta, right? Because these SIs could be
q times beta or 2q times beta. It could be
no, it could be beta plus k or kq, right?
Okay.
Right, exactly. Yeah, so that's not exactly what we want, right? So then, like, what do we do? Like, I mean, here's the issue. We prove that this is exactly beta mod q. It's exactly beta, right? Mod q. But maybe it wraps around mod q. So from looking at this, there's a few ways to solve this. So the first thing you can say is that, okay, remember when we proved what this S bar was, right? When we extracted, we said every coefficient is not bigger than m or something like this, right?
Yeah.
So now every coefficient of S bar is not bigger than m. Okay, so then maybe now you have the inner product, now it's m squared, right? So now you sum up this time. So you can somehow compute what is the maximum this can be in terms of m. Right? And as long as that maximum
is smaller than
q, exactly, we know there's no wraparound that happened. Okay, so that's one thing, right?
Would that be very restrictive on the size of m, or would that make q have to be a lot bigger than m?
Exactly. So here q would have to be like m squared times maybe another m, because we're summing up all of these things. So it's actually quite large, right? I think because this extraction that we had before is a bit too loose. Right? So there's another thing that we've been doing. This is a technique we've really kind of been very useful in lattice-based proofs, is the random projection method, used like the modular version of Johnson-Linden-Strauss. Like if from statistics or from ever seen this? Okay,
no, but I'm sure
the
whiteboard is a great place to talk about it.
Exactly. So let's erase this. We don't need this anymore. So let's forget about. I mean, this is just like a math fact.
Sure. We can also switch sides if you want to write on this side.
No, I don't. Okay. I don't think I'm blocking anything useful here. So let's just say we have some vector s, which is long, right? So s is in like some z to the m, right? And I wanna prove to you that, or at least I want to convince you that s is small. The norm of s is like something small. So what I can do is I can create a random projection of S. So I create a random matrix R. Let's say it's like even negative one. You can have Gaussian thing in here, like normal, like from something from a normal distribution. But if you want to be discrete, what we do is we put -1, 0, 1, with like this is like 1/4, 1/4, 1/2 probability. So just a random matrix -1, 0, 1s. Let's call this R. We multiply by S.
Is there a reason why we choose that sort of randomness or that shape for R?
Because it's kind of like a Gaussian. And normalized, and it's just convenient to. I don't think there's any advantage to taking bigger numbers.
I see.
Okay. And then we have RS equals to T. So now this, let's say, is only 256, dimension 256, and this is quite large. This is our M, And what we're doing, and why it's called random projection, is because we're taking a vector of dimension m, and we're projecting it down to dimension 256 using this random, and this part is random, so this is the random projection. And now what you can actually fairly easily, derive is that if these were like the normal distribution, is that the norm of t is very much related to, is very concentrated around some scaling of the norm of S. So basically, if this norm of t, which is a much smaller dimension, is something, then you can conclude that norm of S is the scaling factor times, within a factor of 2.
So when you say concentrated, we mean sort of the probability. Like, is there some sort of
there is a probability
depending on R here?
Yes, there's a probability over R, right? That so the probability over R that the norm of t is somehow outside this tight bound, depending on the norm of S, is like exponentially small. Okay. So, And so the important thing is that this bound is now like a factor of 2 or 3 or something like this. Maybe from each side, it's maybe a factor of 4 then totally. So once you have t, you know exactly norm of s within a factor of like 4 or something.
Okay.
From up and down, right?
Okay.
And now now that is a much tighter way to bound the coefficients of s than what we had before.
Yeah, the sort of m-square thing.
Yeah, exactly. We don't have this anymore. So all we have to do, for example, one simple thing that we can do is just do another linear. So now the verifier can choose the r somewhere, right? And we prove to it, and we send the t, and we prove to it that rs equals t using, because we already know how to prove linear relations, right?
Okay, I guess I was going to say here again, we could have r here and z. Okay.
That's something we could do. So that's, or you could also maybe a little bit differently if you wanted to. So this would prove that each column is, right? We can also do something
matrix-like.
Yeah, we can do it for each row, for example. Something else to notice, but this is sort of, you didn't even want to mention this because this is super special to the integer case, which will not happen in polynomials, is that this c, right? Now it's 0, 1, but what if you made it -1, 0, 1?
Can it become our r?
Exactly. The c can become our r and kind of serve two purposes. One, to make a commit, to kind of be the challenge for the commitment, and the other one is actually to prove a tighter bound on S.
Okay.
Right. So this, but we don't do this in the polynomial case. So this is kind of like this thing that just shows up in the inefficient constructions, but like in efficient ones, we wouldn't have the chance to use this. It's too bad, but yeah. But anyway, but basically, random projections is the way we prove things that are, we kind of prove.
We prove that there's no wraparound.
Right. So random projections, right? It's almost as good as this, right? We're saying, because we can prove the norm of S is quite concentrated, right? So maybe you would say, maybe we don't even need this. And in some cases, maybe you don't, right? Maybe it's good enough.
This D check.
Maybe you don't even, you won't even need something like this, right? Random projections is, it really depends, right? Like basically in some schemes, for example, in the standardized signature scheme Falcon, you really want the norm to be less than something. And if you allow the norm to be like 4 times as big, now you're losing about 20 bits of security, 50 bits.
Okay.
I don't know. So maybe then you have to change parameters. So if this is not very expensive, then you might as well do this. Or if you really need this, you might do this. Maybe in some situations, you're not just proving norms, right? Here I was just proving norms. Maybe you want to prove some relations, right? Between some quadratic relations, and there you really kind of need prove some exact thing. Well, here it's just integers, but maybe you're right. Maybe I want to prove some quadratic relations. There I really do want to prove that it's like B. It's not the norm doesn't really
and so
have
here
any meaning.
We're proving a quadratic relation, but specifically on the square, right?
Exactly. Yeah, this is a very specific quadratic relation, right? This is the quadratic relation, which is actually the norm, right? But we could have, for example, had a commitment to S, had another commitment to something else, and prove that the inner product of S and S prime is something, right? Maybe that has some meaning for something, right? Yeah. And then it's not really the norm, right? So it's not like, but the norm is like, well, no one cares about the norm. That's not the meaning of what we're proving, right? Yeah. So we would still need to prove this approximate norm to prove there's no wraparound, and then we would prove some inner product relation. Which, it's not like a norm relation. So we actually do need the exact thing, some circuit maybe, or something like this, right? So we really do want it to be some specific value, not just smaller than something.
Yeah. I have a couple of questions for you. Maybe a bit more. So the first one is, are we saying left, right? Because here we have this left multiplication and here the right multiplication.
Exactly.
Cool. Yeah. Then the next question was, why are we using rows of S?
Why are we using rows on the right? On the left.
On the left, yes. Is it just how...
That's just how
the
we can
rules
multiply.
of matrix multiplication.
Yeah, that's just how it works out. So actually, if you think, so what we're really doing is we're really proving things about the rows. The columns thing is just to prove, like on the multiplication on the right, is just to prove that there's a commitment to S. Right. Now, you might ask, okay, why did we need to do both, right? Why not? We have this SC, right? We could have just, this SC is just some we could have made C like lambda or something, and we could have summed up the columns,
Yes.
right? So this would have been exactly this. So for the columns, we could have done multiplication. The problem is that for lattices, you need things to be small, right? So this C had to be small.
I see.
Right? So C being small allows us to prove
The linear relation.
the commitment that this was a commitment to S. And once we know it's S or S bar or whatever, it's a unique commitment, then we can play around, we can multiply whatever we want, right? As long as that commitment is already there, right? You could also say, okay, fine, make these small, and now you can still write, so this wouldn't be lambda to the I, this would be like C sub I, C sub I. Yeah. So you could just, these didn't have to be powers of lambda, right? This could be anything you want for Schwarzschild. The problem there is that the nice thing here, why is it like this? Because these powers, they all kind of canceled out and they all became, they're all between m and minus m, right? Whereas if they were just distinct C's, you would have all m squared possible combinations.
I see,
and
so
now
we have a lot more cross terms.
Exactly, now you're back to m squared.
Right.
I mean, maybe you could make some progress, like, okay, before you started with m squared, now you have m squared over 4. But, in practice,
it's not enough.
This is not what we, probably not enough. And this is, So we really want to go from m squared to m.
Okay. The last question I had is, you often mentioned here we're working over integers, but that's not usually what we want to do, that there's more efficient ways to do things.
Right.
What are those ways? And do we have time to talk about it?
I think we have time to talk about it, but maybe before answering this question, I want to just say one more thing about this. So this gets us a square root, right? And notice that the verifier time is also efficient because the verifier doesn't work with anything that's m squared. It only works with things that are size m. Okay?
Or a constant times
constant times m, exactly. Oh, right. But we may want to make the proof even smaller, right?
Yes.
So then we could either maybe repeat this in cells. So it's pretty similar to a folding scheme, but we don't think of it in those terms. We actually want to build a full sort of snark. So you can either do this, or we think what's more efficient is to feed this into like very compact scheme that's also lattice-based, like Labrador, or there's also kind of Greyhound, which is about polynomial evaluations, but maybe Labrador kind of makes more sense here. And which is the Labrador is linear time verification. But since we already got square root here, maybe in practice it doesn't really matter. Maybe you do want to repeat this once, maybe you don't. One more time, maybe you don't. But I think in practice, maybe just feeding into something that's very compact at this point is good enough. So that's something we do. And of course, we also care about the prover time. Yeah. So the most expensive thing is to compute this thing, this product.
Yeah, these
right.
Cross terms.
And now the naive way, right, is just to multiply them out, right? But each of these, of these individual terms, right? This is the vector of size m. This is the vector of size m. So that's like m operations, right? And if now you have m more of these, that's good. So m.
Yes, we do this n times.
Like this is like a polynomial degree m, right? You multiply it, now you can have like m squared time thing, m squared operations of m things. That's m cubed.
Right.
Which is bigger, which is more than linear, right? If m squared is our linear thing, then m cubed is like to the 3/2, right? Yeah. So we don't want to do that, right? So like this is unavoidable, right? Multiplying these two together, inner product, that's going to be m. Yeah. But the polynomial product that we can do using NTT or FFT, right? And that'll be m log m. So then we'll have m squared log m. Okay. Prover time. Okay. So that's, I think that's kind of, I don't know, unless you want to ask something before we talk about rings. But maybe before we talk about rings, let's just understand what the inefficiencies are here and what we may want to improve upon, right? So here's one inefficiency, right? Is that this C was 128 rows, right? So now we're, okay, it's a constant, but it's 128. So that's quite big.
Columns.
Right, the number of columns is quite big. And the reason we needed 128 columns is because, remember, like whenever we were changing one C, if it was just one column, then there's only there's a 50% chance of the prover cheating. So there's no reason. So so if we could somehow, if the C were not integers, if there was some bigger ring or field, that would be better.
Okay.
That's one thing. The other thing is that these lambdas, right? The lambdas are in ZQ. And I mean, I don't think there's anything you can sort of do, obviously, right? Because this is in ZQ, this is in the same, this polynomial in ZQ, right? So now, because Q, I said it was like 2 to the 32, now you're gonna have to repeat.
Yes,
and actually
if we want more than 32 bits of security.
Right, and parallel repetition maybe in this case is not as trivial as just repeating because some things may go wrong. So that's also, that's an issue. So even if you could repeat, you're still like doing this four times. I guess the other thing is that this matrix A, if this matrix, but that's just your commitment scheme, right? A, if this matrix A is really an integer matrix, multiplication is expensive. If we could somehow put some structure into it, we could have cheaper multiplication. So using polynomial rings, that's what we use in lattice cryptography. We've been using it since '96 when the entry encryption scheme was kind of introduced lattice encryption using over polynomial rings. So this is what just the rings themselves have changed, but the idea that rings are useful is kind of endured.
Okay. So what do they look like? And
so let's erase all of this and just do a little bit about polynomial rings. Good. So polynomial rings we use in lattice cryptography are usually of this form. I'll explain what they are, but we write like RQ equals ZQ adjoined X mod X to the D plus 1. And this D is a power of 2.
Okay.
So
what is this and why?
Yes. Okay. So first, what is ZQX? So ZQX are just polynomials. So ZQX is just the set A0 plus A1x plus A2x squared,
etc.
where x is your indeterminate. We're not plugging anything into x.
And our A's are in ZQ. The coefficients?
The coefficients are in ZQ, exactly. A's are in ZQ.
Yeah.
Okay. So now adding polynomials together, we just add the coefficients, easy. Multiplication, I mean, doable.
Yeah.
Okay, we did that before, right? Okay, so multiplication, addition, okay, that's this ring. Now this, mod x to the d plus 1. Well, this is actually not much different than what this q is, right? So if you know what mod q is, every time you see q, you just make it 0, you wrap around. So basically q equals 0.
Yeah.
And here I'm just saying x to the d equals -1. So x to the d plus 1 equals 0.
Okay.
So x to the d minus 1. So whenever, let's say, you multiply two polynomials, and now some degree is bigger than d, that x to the d becomes -1. So for example, so if you had like the fourth and d was 4, let's say d equals 4, then this a to the fourth becomes
-1,
becomes a0 minus a4 plus a1x. Okay. So all the polynomials in this ring are really just have coefficients in ZQ and of degree less than d. That's it. So when you add them, you just add the coefficients. There's never any wraparound mod x to the d. When you multiply them, you're going to get x to the d, so you have to kind of bring it back.
Sounds good.
Okay, so, and now just kind of understand why did I say power of 2? Because for security, we want this polynomial, x to the d plus 1, to be irreducible over zx.
Okay.
So basically, you cannot factor x to the d plus 1 over as a, so it's irreducible, and it turns out that x to the d plus 1 is only irreducible if it's power of 2. Now, it could be completely splittable mod q, zqx. It depends on how you pick it, right? But for security, we really need it to not split over z, over zx.
I'll take your word for it. Like I don't see the intuition, but I don't think
it's actually I would say it's very surprising, right? That it's okay that it splits mod ZQ,
Yes,
but it's not okay that it splits ZX. And this was just a historical thing, just one of these big kind of things that came out of these worst case to average case reductions, where you, even though they're completely, like for parameter setting, they're completely useless.
Right.
What they did say is like, actually you can prove that lattice, this cis over polynomial rings, learning with errors, which is basically like homogeneous cis over polynomial rings, is hard whenever, at least we can have this reduction when this is irreducible over ZX.
Wow.
But not when it's like it just fails, it just doesn't work if it's not irreducible, or it's weaker, much weaker. But ZQ, it's kind of like, well, set it to wherever you want. That's not part of the reduction. Part of the reduction doesn't care. You can set, which I would say is very surprising. Very surprising. But that's the kind of the big utility that came out of those reductions. That you say, okay, actually Q doesn't matter. And when you try to apply the same attacks, like when things split, when they split mod Q, they don't work. And there is some mathematical reason.
I'm sure.
But it's very surprising. But now it kind of that this was this scaffolding, right? These security processes. Okay, here's the thing you want to work with. Now actually set the parameters. Now we don't care about these worst case problems.
We just
use the average case problems that these worst case problems kind of gave us and the parameters. Because in some sense, like having worst case problems, it's kind of useless. Like, what is the worst case instance? How do I know how my algorithm works on a...
Yes.
So with average case, much easier to work with, and this is exactly what we want for crypto anyway. Okay, but
we digress.
Digress. Okay. Proofs were important. Okay.
Yes.
So now the cis problem over the ring, over rings, or we call module cis, and this is actually what the standards like Kyber and dilithium and are based on, is very similar to before, right? So now you have A, which is a random matrix in RQ to the, let's say,
again,
n by m, but now n does not have to be 512.
Okay.
So what we care about, like, is our n times d has to be the same kind of dimension as this has to be this 512 or 1024, right? So before the security parameter was n, now it's n times d. Okay. So if your ring here, if this d is like 256.
So here, correct me if this intuition is wrong. So every element of A is actually d coefficients.
Yes,
right.
Exactly.
So now d times n needs to be big and not just n.
Exactly.
Right. Okay.
Exactly.
Because d times n is the number of coefficients.
Yes, exactly.
Yeah. Cool.
Okay, and then we have our S, which is in R to the M, with norm of S small. And norm is exactly how you just over the coefficients. There are some other ways to compute the norm, but for this ring, that's equal. That's good enough. Good. It's perfect mathematical definition. Norm of S is small, so the sum of the norm of the coefficients is small, just like before. And the hard problem is f of A of S equals t. That's the one-way function, right?
And it's again the product
is defined as AS.
Okay. And then we have multiplication of ring elements.
Yes, now we have multiplication of ring elements. Exactly. Okay.
And this gives us efficiency Y.
Okay, so let's kind of we're not going to redo the whole protocol, but just kind of some parts of it we can redo. All right. So again, let's say we're trying to commit to S to a lot of coefficients and to prove that the coefficients are small, right? The norm is small. All right. So remember the first step, right? We had we divide our A in, we still have our square matrix S. We kind of put the S into, split it up, right? And we get our T. But now these are all polynomial, vectors of polynomials, right?
Yes.
Okay. And remember the first step was he sends a matrix C.
Yes. The challenge.
C. And then I send Z equals SC. All right. So before, we said this could not be a vector.
We had this problem that the prover could cheat one out of two.
Exactly. Because each coefficient had only like one possibility. It had two possibilities, 0 or 1. So now here, the big advantage, and this is why like these lattice-based proofs are much more efficient with rings, is that you could have, because before you couldn't have a lot of small elements in your ring, right? Because if you're over the integers, if you want, an element less than, some b, bound b, there's b of them.
Yes.
Or 2b, because there's minus, right? But now if you're over polynomial rings, the number of small elements is now actually quite large, right? You can have 2 to the d elements with 0, 1 coefficients.
Right, yes.
And you can actually multiply by them, right? So now your C could be a vector of small polynomials. Right? Because now to extract, you would basically you would fix all the polynomials except one and flip that one.
Right.
Okay, and that one has to, now if there's like 2 to the 128 of them, at least, then the adversarial prover or any prover has to be able to reply correctly to at least 2 of them.
I see.
Now, there is going to be a bit of an issue. We're not going to be quite extracting the same thing as before, because before, remember, we had the C minus C prime. It was always like 1 or minus 1.
Yes.
So then we ended up with like AZ equals TI times, so we had A times Z minus Z prime equals TI C minus C prime, right? And this would either 0 or 1.
Yeah. Sorry, 1 or minus 1.
1 or minus 1. Yes, sorry. Thank you. But now it's not, and so because it's 1 or minus 1, we could get rid of this and we said plus or minus TI. Now, if it's a polynomial, we don't quite get
this.
They
don't cancel out.
They don't. Now it's just going to be TI times some C with small coefficients, but it's not, we didn't really prove that AS equals T. We proved that AS equals T times C. But that's okay, because it still proves that there's a unique S bar that can satisfy this relation for a small. Okay? So basically S bar divided by C bar is going to be unique.
Yes.
Right? It's not going to be small, but it's unique. Okay, but that's kind of all we needed from the right side of this left-right proof.
Can we always divide by C bar?
We make sure that it's invertible. Yes. So this is important. This is why also we don't want, in the way we do the zero knowledge proofs, we don't want this. So before we used to do it differently. We used to put our coefficient, the things we care about, the secrets, in the NTT, in the Chinese remainder for when this polynomial split a lot in here, and we put all our things in there, and because it was nice because you could do component-wise multiplication. But then we realized, no, this is kind of not the optimal thing to do, because if it split too much, then the C cannot be too big. The entropy cannot be too large. So we actually now prove things not in the infinity norm, but we prove L2 norm, and this is. I will show you why this is okay. But anyway, let's.
Yes, this sounds very advanced compared to where we are so far.
Yeah, a little bit. Yeah, kind of a
looking ahead.
Looking ahead. Yeah, looking ahead. But yes, very good point. You must choose a C so that the differences are invertible, right? Okay. So then from the right side, you still get a commitment. You still get there is a unique S, so that AS equals T, where it has this properties that S is small and then S times C is small. Okay, good. We have this. It's going to be a little more difficult to prove that Z really is SC. But that can be done once we do actually the right. That's okay. We have to do something else. That's no problem. I mean, it's something, but yeah, it can be done. The thing about the multiplying by lambdas,
the left side,
that's kind of almost completely for free. You get a bigger lambda because you can use a bigger ring, right? But now the question is, what are we actually proving? If you remember before, we were proving the sum of SI times
this inner product with itself.
This inner product we proved, and then we proved that this was some beta, right? Where beta was an integer.
Yeah.
Now this is a bit different, right? Now these are polynomials, so we're actually proving polynomial products.
Yes.
And it's going to be some polynomial, but this is not what we want.
We wanted the norm.
We wanted the norm. We wanted this coefficients, and now we're getting this polynomial product. Okay, so this is now the little trick that we've been using for the last couple of years, and this is why we switched from kind of the NTT representation, the Chinese remainder representation, to actually just putting what we care about in the coefficients. Okay. So let's just make an example. We can maybe stop after this too.
Sounds good.
So let's say we work over, let's say D is 4, just an example, right? So we have some S equals S0 plus S1x, x squared plus S3x cubed. Okay, so that's our some polynomial, right? And we're basically getting many polynomial products of this form, right? So S times itself plus, some other S by itself, right? Okay, but we want the norm. We want S0 squared plus S1 squared plus S2 squared plus S3 squared. If we just multiply S by itself, we're not getting that.
Yeah.
But you actually can multiply S by something related to S. So we define this automorphism of S.
Okay.
Right? It's just a way to flip coefficient, but it doesn't matter.
Yeah.
So it's actually we define it as 0 minus S3x minus S2x squared minus S1x cubed. So we fix this one. So you can think of fix this one and then kind of rotate it. If you want to think, algebraically what this is actually S. So this is S of x, right? This is S of x minus 1. Because if you plug in minus 1 here, because remember, minus 1 is equivalent to
1 over? Oh no, minus 1 was equivalent to...
No, x inverse.
Oh, that I don't know, no.
So yeah, so basically, for example, so x inverse is actually x cubed, right? Because like x or minus x cubed, because x times what is 1. X times minus x cubed equals 1. Right?
Oh, yes.
So
of course.
So yeah, or maybe this is a silly way to write s of minus x cubed, right?
Okay.
But like x minus 1 is kind of, I'm writing it because maybe we'll think back of what we were doing before with these powers of lambda.
Of lambda, I see.
It's kind of similar, right? So this is actually x to the minus 1. So if you plug in x cubed minus x cubed for every x here, right? So now you have plus s3x cubed plus, right?
Yeah.
Right? So this is actually x to the x minus 1. And now, if you multiply s of x times phi of s, you'll get in the constant coefficient, right? So what are you going to get? You're going to get S0 times S0.
And anything that's power 4, right?
Exactly. The negative of anything power 4. So now you have S1 times
minus
S1.
And then we take the negative of that.
Plus S2
minus S2.
Plus S3 squared.
And lo
plus
and behold.
something times x, I don't care what it is, plus something x squared. And that's exactly what...
Something x cubed.
Sorry?
And something x cubed.
Yeah, plus something x cubed. Yeah.
Just for completeness.
Yeah, plus something, not leaving one out.
Yeah.
Right. So the constant coefficient is going to be exactly the norm. So all we have to prove is that in the constant coefficient, so this will be some polynomial, we can fill in the other coefficients. We can send them ahead of time, something like that. And the constant coefficient is exactly what we're looking for.
The claim.
Right? So, and like this cancellation, right, of this x.
Very reminiscent of the lambda thing.
Exactly. That's where I wrote like the x to the minus 1, right? Because this would be x to the minus 1, this would be x to the minus 2, this would be, so you can write this as like, plus s3x to the
minus 3.
Minus 3, right? X. This is plus s2x to the minus 2 plus s1. Right? And it would just cancel. So, and that would be exactly the same as there, except here we have this, the powers don't, we don't have like between minus 3 and 3 because we can actually reduce mod x to the 4th plus 1. There we could not. But this idea of things kind of canceling out and being put in the constant, the thing you're looking for is in the constant coefficient, it's the same idea. Right, like we didn't really realize it that way. It wasn't come up, but you kind of come up with this and say,
always in hindsight that we realize the similarities.
I'm not sure what to do with the similarity, but just like kind of knows, it's kind of it's just kind of there and nice to know. So basically, we can prove something meaningful about the norms by proving this, and we're saving quite a bit because we now don't have this 128 thing, and we don't have to repeat because our C, because our C is just a vector, and we don't have to repeat because our lambda is now coming from a bigger ring.
It's not just from Q, it's from this ring. Okay.
And of course the A is now, like multiplication, this A times S is also now more efficient because now you're not multiplying just a random a, you're actually multiplying polynomials, which is a more efficient multiplication. You're saying instead of like n squared, it becomes n log n.
Okay.
So you're saving quite a bit. And all the linear relations you may want to prove, if we're proving like lattice, something about lattice schemes will be using these same polynomials, right? So it's already kind of, you're using the same structure. The thing you're proving has the same structure as your proof.
Yeah.
So that's already kind of, there's no, like, you don't have to do any conversion or compilation, right? Yeah. You're really doing that. So that's kind of where we are. Yeah, with the lattice-based thing, of course, yeah, the improvements, of course, implementation is happening and improvements are happening. But yeah, the high level, the bird's eye thing is this kind of what I explained. Hopefully, it's at least the high level is understandable.
Yeah, thanks. So to summarize, kind of the session, we saw hard lattice problems, the cis problem. We saw how to get commitments out of it, the I-type commitment.
Yes.
Then we saw this AS equals T sort of proof of knowledge that I've committed to something.
Correct.
We saw why having just a small challenge was a problem, so we had to take these multiple columns of challenges.
That's only for the integer case.
Yeah, for the integer case.
Which will not happen.
I'm just citing through, I guess, what we did. Right. Then we looked at how to get a tight bound on, or prove a specific norm for our S, the S that was extracted. Yeah. With this left-right technique, and now we've looked at like how to make all this more efficient with rings.
Yeah,
lovely.
Yeah,
thank you very much, Vadim.
Oh, my pleasure. Thank you, Nick.